Hey, welcome back to my living room. So, we are back here because my wife is working in the office and I am watching the babies. They're napping and you can see my baby monitor over there. And I dressed put on a dress shirt on to pretend like I'm a professional, yet I'm still wearing my pajamas. So, that's how modern professionalism works. Or at least in the pandemic. In any case, welcome, and let's talk about this. I keep asking why I even signed up for this again. You know, because I mean, like, this is I just got out of this crazy spring semester where we did this online switch in the middle of the semester. And now I'm back into this, and hold on one second. Garbage collection. Yeah, the joys of working from home. And I guess, so I keep asking myself why do this again for the summer, and I have to keep reminding myself why. So I mean, there were several things that went through my mind. Is one, when everybody signed up for summer teaching, we had no idea that this pandemic was going to happen, and so there was no thought of this being online. So people were just suggesting to do a, sorry, cat's scratching everything. So people were just thinking of doing they were going to do a regular, lecture in differential equations. And so, and then when it came out that we were gonna have to do this all online again, at least one of the professors who wanted to teach this class canceled because they didn't want to go through all this stuff again. Now I know other professors had actually even just sort of checked out in the middle of spring. I had heard rumors of some professors just giving their lecture notes and saying, have at it, and then they just gave them a final at the end of the semester. And so I mean, combination of the class not even being offered and other people not really putting any effort into these lectures, I just made me feel bad for the students, and so I figured I'd give you all an opportunity to have a shot at differential equations over the summer, and hopefully this lecture format will help. At the same time, I get to fill out my YouTube channel with a full set of differential equations lectures, which makes me feel nice and solid and complete. Just having the Laplace transform up there, the latter third of the class, just didn't make a whole lot of sense. So what are we doing today? So today we are going to be going over just a whole bunch of random differential equations. These are all actually systems of differential equations, and so if that doesn't seem to click with you, don't worry about it. This isn't anything that I'm going to be testing you on, but we just went through a whole bunch of definitions of equations of writing down formulas for what we call a differential equation. And but it didn't really talk about what they mean. So this lecture is just going to go over 3 different examples. One is about pendulum motion, straight out of control theory. Or physics, if you like. The control theory aspect is trying to balance a pendulum upside down, and so in the middle of this I'm going to show you a clip from a video that I have a link in the description if you want to see more of that. And this was by a group external to me, but this is definitely something that you would end up doing if you took undergraduate lab in control theory. This would be the sort of system you would look at. The next thing I look at is what are called the Lotka-Volterra equations. These are also known as predator-prey equations, and they come from biology. And these are so they're the basic model of ecology, and you could have bunnies or wolves, or you can have any sort of predation on prey, and etc. You can even have this on multiple levels. You can have a predator of predators of predators, and then one bottom prey, which might be a flower that is attacked by I don't know, something that likes to eat flowers, and then that thing is attacked by something that likes to eat things that like to eat things that eat flowers. I don't know. I'm not an ecologist. That is not my thing. I'm a mathematician. Give me the equations, I'll tell you what they mean. But I mean, like, yeah. Anyway, then the last one you might find interesting in a given pandemic. It basically explains one model for infectious disease spread, and this is called the SIR model. And this is what a lot of people are talking about when they talk about COVID-19. And this is one really basic version of the model that they have. The real-world models for this sort of thing use the same sort of concepts that you have of SIR. But they also need to integrate in, like, multiple communities connected, adapted to data, fit parameters, etc. And this is what would come up in what was called systems theory. And also a control theory aspect of that would be where you will kill connections between different communities. And so one way of doing that also would be to do self-isolation, which will limit the amount of spread that happens from infectious people infecting susceptible people. And so that will dampen down one of the parameters, and so therefore you could even integrate in some control theory in there as well. So this just gives you an idea of how differential equations are used in practice, and just cat. So it tells you how they're used in practice. And and so hopefully you want to go? Okay. And then hopefully I'll give you a better idea of what to think about while we're actually going through the rest of the class. If you don't understand the actual individual techniques I'm doing, or if you don't understand my explanations of these equations, don't worry, this isn't going to be on a test. This is just for your sort of edification, to sort of help you get a conceptual idea of how differential equations work. And then next lecture we will jump in, and I'm going to do actually a project out of chapter 1 as a lecture, and this is called Picard iteration, which I think is a very nice low-level attempt at approximating the solution to a differential equation. Because chapter 1 is really just sort of, the idea is to get sort of a qualitative and sometimes quantitative idea of how to approach a differential equation rather than actually solving it, which is the whole rest of the class. And so we'll take this step by step. I'm not trying to rush you guys. I know you guys are learning from home. You might have the best learning environment at home, but hopefully it's a little bit, if you've decided to take a summer course that's online, you're a little bit more prepared for that than you were back in spring. Yeah. In any case, I hope you enjoyed the lecture, and let's jump into it. Okay, welcome back to class. So this is our second lecture in class. Hold on. Changes, margins, data template. Let's get some lines in here. Change. There we go. Okay. So here, this is going to be lecture 2. And this is just us playing with differential equations. So the last lecture sped right through the definitions out of section 1.1 in Nagelsaff and Snyder's book, and also the definitions that came with solutions to differential equations out of section 1.2. So here, instead of diving into section 1.3 and giving you more homework, I thought it'd be more instructive to just talk about a whole bunch of differential equations. And so I think it'd be more fun to just try some new examples, give you some intuition as to like how you can play with them and things you can do. A lot of these techniques I'm going to show you, you don't necessarily need to memorize and figure out how to do it. I just want to show you how differential equations show up in the real world, and and some ideas of what to do with them. Okay, so let's take a look at this first one, and this gives me an excuse to jump into a book I just got. It was an evaluation copy from Pearson of nonlinear systems, which is a big control theory book, and there's this one topic that's kind of fun that comes up in there. It's about pendulums. It seems kind of a dumb sort of thing, but basically we have a rigid arm. and of length L. And yeah, we're basically letting this thing dangle. It has a pivot point here, and there's some sort of dongle or something. What do they call this in the book? They call it a bobble? A bob. All right, they call it a bob. Hey, Bob. This is a Bob. Actually named Robert, but who cares? All right. So the idea is that we have some sort of, we've secured this pendulum to this point, and then we have this angle theta. And you can actually describe the change of theta with respect to the differential equation. Now you can do this using straight physics, and I'm not going to get into those details, but here's ultimately what you get. You get m times L times theta double prime is equal to minus mg sine of theta minus k L of theta prime. Okay, so L is pretty clear what that is. M is the mass of the Bob, mass of Robert. And let's see, what else? G is a force of gravity, or G is gravitational constant. So that's, you know, pretty standard. K is a friction coefficient. And so basically, as this thing spins around this bit here, you know, there's going to be some resistance coming back against it based on how fast it's going. And so that's why we have just theta prime there. Now you remember, of course, you know, from physics, we get the force is equal to mass times acceleration, right? And so basically this is where the theta double prime is coming from, and well, this mass too. And so that's what we get. Okay, and so basically the idea is that, you know, this thing is going to be moving and it's going to stay tangent here, and so it makes it really convenient to just talk about this in terms of theta. Now, there's a couple of things that we can sort of intuit about this. So there's going to be two places where we're going to have something that we would call stability. So for instance, if I were to just dangle the dongle, the Bob, straight below it, it's not going anywhere, not unless I hit it on the side. And so this configuration would be, say, a stable configuration. Because if you start there, you won't change after that. There happens to be another one, and so this is a stable, and in particular we call this the equilibrium. And here would be another equilibrium when we stand it straight on its head, but this would be unstable, right? Any bump would make it fall. I mean, people find that pretty intuitive, I think. But now let's see what we do in order to find that. So basically, we would say we have an equilibrium point if we have, say, dy dt is equal to, say, f of y, and then if there's a y naught such that f of y naught is equal to 0, then y naught is an equilibrium point. Okay, and so I guess my experience in engineering just makes me not see that this is an issue, but the dot form is just saying this is a second derivative with respect to time, right? So this is a standard engineering notation. Don't get too confused. So we just put a dot every time we want another time derivative. But yeah, so this is how you'd see differential equations popping up in, say, control theory, mechanics, and electrical engineering, places like this. So we change this for this because it's easier to write. Okay, So this is a first order equation though, right? Remember, if we have only one derivative in our differential equation, means it's a first order equation. This is a second order equation. Right, so that's this whole equilibrium point thing maybe isn't making so much sense in this case. So why don't we see how we can actually convert this into being a first order equation? And this is an interesting little trick that you see a lot happening in engineering. So basically what we're going to do is we're going to trade a one variable ODE, ordinary differential equation, that's second order, for a two variable ODE that is first order. And the way you do it is basically you say, I'm going to declare some random variable, and so I'm going to say x1 is going to, our first variable is going to be just say so I'm going to say my first variable, the derivative of that is just going to be x2, and then I'm going to say this derivative of my second variable is going to be what we're actually talking about. So I'm going to say divide both sides by ml, and so then that's going to give me minus g over L sine of theta, or gonna say, instead of theta, I'm gonna say x1 minus k L, and now instead of theta prime, I have x1, which is supposed to play the role of theta. I'm just going to put x2, right? And so there you go. We would actually have a two variable system, but first order, only one thing. So we're basically, that's what we end up having. So now we can actually ask again now, we'd have a new system. So we'd call x, and this would be sort of our stacked version. And so, and x dot would then be x2 and then minus g over L sine of x1 minus k L x2, and then this is what we call, say, we'll call it big F of x. So now we can take this guy and we can come over here. Right, and yeah, so I can go ahead and set this equal to 0, and that will give me an equilibrium for this system. So I could say when is f of x equal to 0? Well, then that will tell me 1, we have x2 minus g over L sine of x1 minus k L x2 would be equal to, say, 0 and 0. And then that tells me then that x2 is equal to 0, just by matching this first equation. And by matching the second equation, well, we already know that x2 is equal to 0, so that goes away. And so we're left with minus g over L sine of x1 is equal to 0. And since these are all just some fixed constants, this tells me that sine of x1 is equal to 0, or it just tells me that x1 is equal to 0, right? So, but it might not only be 0. For instance, it could also be, say, pi, or 2 pi, or minus pi. And so basically it says that x1 could be, k would be unfortunate, say s times pi for s equals, say, minus 2, minus 1, 0, 1, 2,
etc. Right? So it'll be something like that. Okay, so that tells me, remember x1 was supposed to play the role of theta. So that tells me that we have equilibriums at theta is equal to, each one of these points. So say 0 and pi, and then we know just geometrically it's going to be the same position over and over again, right? Because it's going in a circle. So we have equilibrium here, and that's 0. And then we have another one at pi up here. And so there you go. Now we can go in and do a further analysis, see whether or not it's unstable or stable, but I think I threw a lot at you right here. So basically this is how you'd find that sort of thing. So we see that this actually backs up our intuition initially about this pendulum. Now what I want to show you now in say this square right here is a neat little control theory experiment where basically engineers in say a control theory 101 course will set up this little robot, and they'll put a pendulum, what's called an inverted pendulum, on it. And the idea is that they want to design a control algorithm that moves this platform back and forth, but keeps this guy perfectly vertical. And in the video I'm going to show you they actually even stack some cups and stuff. I'm only going to show you an excerpt, and the rest you can find in the links below. And yeah, I think it's pretty cool. And so this is called an inverted pendulum. And it's a neat little control theory problem. And so if you go into control theory and you do the laboratory, this is probably going to be something you're going to try to set up. Okay, so that's nice. Now let's talk about something else. And this is called the Lotka-Volterra equations. So this is another multivariable system. It turns out most applied systems are multivariable. We're just going to cover single variable problems mostly in this class and just solve them that way. But I wanted to go over a few of these important things. So this comes from biology, and the idea is it corresponds to sort of a predator-prey model. So has two names: Lotka-Volterra for the mathematicians who are working on it, and predator-prey is more common. So, so the differential equation is like this. So it's dx by dt is equal to alpha x minus beta xy. And we have dy dt is equal to delta xy minus gamma y. And this is straight from Wikipedia. So basically our variables here, x and y are dependent variables. And t is an independent variable. And alpha, beta, delta, and gamma are all constants. Okay, so let's talk about what this is and why this model actually makes sense. So generally speaking, we're thinking of this as our prey. Animal is our predator. Okay. So how does this population work? So let's say we had no predators at all. And so so we can talk about the no predators problem right here. So no predator, we'd have dx by dt is equal to alpha x. Now, this has a very easy solution. This would tell us that x of t is equal to e to the alpha t. So basically we'd have exponential growth of our population. Right? Alpha could represent all sorts of things like how much food you have in the environment, how the reproduction rate, like are they like humans where we can, our offspring can't actually reproduce until they're, say, in their teens, and likely even later than that, or are they like a rabbit who's gonna reproduce super fast? So that's what all these could be. So this is what happens if you don't have a predator. Now, what happens when you have predators? Well, let's say so we have dx by dt. How does this change? Well, okay, so your prey are still going to be reproducing. They're not going to be like, oh no, there's a predator in the area, I can't reproduce. No, they're gonna reproduce the way they always would. But sometimes you're going to lose some. And so some are going to be lost to predation, and so minus beta times xy, where beta is another quantity. So why xy is the question. So if you think about it, let's say let's make triangles our preys. We can put little bunny ears on them if we want to think of them as bunnies. And let's have, say, circles for our wolves. All right, so we have a bad wolf here, yeah, and that's a wolf, right? I don't know. Anyway, all right, so that's a wolf, and we have bunnies. So now, why x times y? So the idea is that the total number of ways that these guys can run into each other. Well, this bunny can run into either one of these two, this bunny can run into either one of these two, and this bunny can run into either one of these two. And how many different connections are there? There's going to be 1, 2, 3, 4, 5, 6. And so total number of interactions is, number of bunnies times the number of wolves. Right? But now every time they bump into each other, well, they're not going to, wolf isn't going to eat a bunny every time. Sometimes the bunnies are pretty fast. Sometimes the wolf just ate another bunny. It isn't really hungry right now. So, you could say it only eats bunnies. Through these interactions, only like 1 out of, say, 6 times does a bunny get eaten, right? So, maybe these interactions don't actually happen all that frequently. Maybe this only happens like once every week. So we can say, if this was in days, we say 1/7, and so then that's where this beta term would come from. It's just the probability of so the total number of interactions that you can have, and something like the probability of it resulting in the death of a bunny. And nobody wants dead bunnies. I mean, that's just bad. So that's what. Let me clear this up a little bit. So it's not literally going to be like this number here, and etc. But that just gives you a sort of a intuition of what's going on, and so that results in the death of a bunny. So we'd decrease it from the population of the prey. Okay, now let's look at what happens to prey. How many predators do we have? Well, if I take a look at my predator equation, we have the increase in predators. So delta y. I should say that these constants are all positive, by the way. So what happens? How do we get more predators? Well, since the predators eat only prey, it turns out that they can only reproduce if they have the energy to reproduce, which means that they've eaten a bunny. So unlike the bunnies, which are just subsisting on the environment, the predator subsists on the bunny itself. So basically, we have the interactions that come into play, And delta here is saying like, all right, well, if this interaction happens, this is how much energy that they're going to have, and this is how much more likely they are to mate. And given that they're mating, how likely it is that they're going to actually produce offspring. That's sort of what that delta is going to play in there. Okay, so then otherwise, if there aren't any, otherwise they do die from, say, natural causes. They don't live forever. So this is going to be, say, proportional, like, once every 30 years a wolf dies or something like that. And so then the proportion of wolves times how many wolves there are, tells you how many wolves we're losing at any given time. Notice that if we didn't have this term, we would just slowly have a die-off of our wolves. Okay, cool. So this is the predator-prey equation, the Lotka-Volterra equations. And if you take a look at them, it's kind of neat. Like they basically form this like loop, this sort of cycle that's sort of what we call a limit cycle in the system, where basically sometimes you'll end up having a whole lot of bunnies, and then if you have a whole lot of bunnies, well, you're going to end up having a heck of a lot of wolves that come out of that. And then, but once the wolves eat too many of the bunnies, back over here, so bunnies decreasing, then the wolves will end up start decreasing. And then once the wolves have decreased enough, bunnies will increase, and it comes up over here. And then once there's a lot of bunnies, the wolves start increasing, etc. And so I'll show you a simulation like that after we get through all these notes. But yeah, so that's sort of how that goes. Yeah, and let's see. So now let's talk about something that's like really important to us right now, and this is the SIR model of infectious diseases. All right, and so you guys we're sort of getting the idea. This is the COVID-19 models. So this isn't what I'm showing you is not specifically the COVID-19 model. This is just a general model for infectious diseases and generally how people think of them. And so what is SI and R? So S stands for susceptible. You need to look how to spell that. Let's see. Since I barely got through high school, I am left with rather poor penmanship and spelling skills. Who knows? All right, so susceptible. SUSCEPTIBLE. If I was thrown that on the spelling bee, I would have just died. All right, I is infected. I can spell that. I've watched enough zombie movies. And R is recovered. And so the idea is that we're looking to model how many infected people we have, how much this is going to change based on how many susceptible people we have in the environment, and then we're going to have a whole bunch of people are becoming immune because they're recovering. And so there's going to be, we have S, I, and R. These are going to be our variables, our dependent variables. And T is our independent variable. And then we have another one, a sort of fixed constant, is that the total population is included in all the set. So your population, it can be partitioned into groups of susceptible people, infected people, and recovered people, where recovered might also mean dead. Okay, so let's take a look. So what is the model that people use for this? And we can do a breakdown of that too. So ds by dt is equal to minus beta times s times I divided by n. Then we have another one, di by dt is equal to beta again times is divided by n minus gamma I. And then we have recovered. Dr by dt is equal to gamma I. Okay. So one thing to check, this is constant, n. And so if I were to add all these equations together, then I should get 0 back, right? And certainly that's true. If I add dr dt to I dt, then this will go away, and this will go away because they cancel. And this term and this term match and are opposite, and so it would cancel. And so if I add all these together, then I do ultimately get 0, because if I take the time derivative of a constant, n, I get 0, right? And so if all these guys added together form a constant, then that's what we get. Okay, so good. So that's a rational check of this thing. Okay, now let's talk about exactly what each of these, the role that each of these guys play, and what their equations do. Right, so you get the idea of infected, right? So basically the idea is that infected people infect susceptible people. Oh my goodness. Susceptible people. There. I made it through that one. All right. So infected people infect susceptible people, right? So just like what we have with the predator-prey model, the number of interactions that you can have between a susceptible person and an infected person is a product of the two. And so basically, and then there's some sort of proportionality constant that talks about what is the odds that they're going to get infected based on, I don't know, whether or not the people generally wear masks or etc. By the way, this is roughly where the role of what they call the R0 would come in. So like for instance, for COVID-19, the R0, I believe, was estimated at 3. So basically one individual has the likelihood to infect 3 other individuals. And that's past the threshold for what would be called a pandemic. I think the flu is a little bit higher than 1 for R0. So like one person will infect like 1.5 people. And so that keeps it from becoming like this pandemic like what we're having now. So yeah, okay, so then S times I is the total number of interactions that you can have, and this is the likelihood that a single interaction will bring on an infection. And so why do we have a negative here? Well, that's because this is the number of susceptible people, and if a susceptible person gets infected, they move out of this class and they move into this class. So now let's take a look at the infected thing. So this is exactly the same as this, because once you leave this group, you go into this group, right? So that's pretty easy. Now, it's after a certain amount of time, just like wolves would die out after a certain amount of time, infected people recover after a certain amount of time, or they pass away. And so you're going to have a decrease in the number of infected people and over time. Now, after somebody has recovered and we have a decrease and you're leaving the infected group, well, the idea is that generally speaking, you can't get reinfected. And so you go into this recovered group. So recovered group just grows proportional to how many infected people there are. So basically each time somebody leaves this group, they go into this group. And since you stay recovered in the time frame that we care about for this model, then you don't need, then you're not going to, sorry. And since a recovered person is going to stay recovered, they don't move back into this class and they don't move back into this class. So recovered only increases, where unfortunately recovered also could include dead people. So that is the SIR model. And so basically the idea is that you have S, you have I, and you have R. And the idea is that S goes over to here, and this happens at this rate. So number of interactions times the probability of this happening, and divided by n as a normalization. And then we have I goes to recovered, and this happens proportional to I. And since we don't have a link that goes from here to here or here to here, recovered just sort of accumulates the population. And so that's actually, generally speaking, what they call would be like herd mentality, right? Or herd immunity, sorry. Is that you would end up having so many recovered people and that can't get reinfected, that there's actually not enough infected people to get susceptible people, I guess. I'm not a infectious disease person. I do understand the model though. In any case, yeah, there's actually, we have a bunch of people who work at our university on these sort of problems, and I am talking to a few people on various problems related to this and data. And so if you're curious, I'd be happy to give you the contact. But yeah, so that's 3 different differential equations that we care about. One came from, say, control theory or generally physics, and showed you this neat little video with the inverted pendulum, and then the rest came from biology. So we had the Lotka-Volterra equations, and we also had the SIR model of infectious diseases. So, in any case, yeah. Hope you enjoyed, and I guess now I'll show you a bunch of Matlab simulations, and then we'll call it a day.
It's late at night, and it's the only time I can find with the baby's quiet that I can get this done. So here we go. My wife's playing Overwatch in the background, so if you hear that, if you hear screaming in the background, that's not anybody I know, so it's okay. Alright, so what I'm going to do is I'm going to just show you a bit of code I typed up, and show you some plots that kick out of it for the Lotka-Volterra equation, and also the, what was it again? Something, it's like, I don't know, it's way past my bedtime. In any case, oh yeah, the SIR model, yeah. Alright, let's do this, and hopefully I can stay coherent. We'll see. Alright, so let's get a screen recording going. I'll do this segment here, and segment here. Let's see, I am just talking to myself right now because you can't see what I'm doing, but it's okay. There we go. Alright, and options, built-in microphone, yep. And good. Alright, screen recording going. I think it's the first time I'm doing this, so bear with me. Okay, so what we have here is a bit of Matlab code that I put together. It's really not that big, and so I have this thing here I call witch plot, and that will toggle between 2 different situations. So I have the SIR model, this is the susceptible, infected, and recovered model, and I also have the Lotka-Volterra model that we're going to check on. And I did something cute, and I made it so it does a sort of draw now sort of thing. So it draws it as an animation, which is not something I've really done before. So that's fun. And so right now I have it set to the first plot, and this is a Lotka-Volterra equation. And so you see it, these are my birth rates, my prey death rates, predator birth rate and predator death rate. These coefficients I actually pulled from Wikipedia. I tried putting it in my own, but honestly it's easy to make your population go extinct. And so, so yeah, credit to Wikipedia there. What you see here is the equation itself. So this is a Matlab function. This is a inline function that I made, where we put in alpha, beta, delta, and gamma. And here x1 and x2 play the role of x and y, respectively. The idea is that this is just sort of x1 and x2 are just sort of in a vector, and that's sort of how Matlab works. It's the matrix laboratory, and so generally everything has to be thought of as a matrix in some way. So so here is my initial value, just started at 1, 2. Our initial prey population is 1, probably in the thousands, probably not just 1, because you're not going to reproduce if you just have 1 rabbit. Although you'd be surprised, rabbits reproduce a lot. And then 2, probably 2,000 predators, something like that. I didn't really define a scale, but it gives you an idea of how this works. Rk4 method, this is something I coded up myself. This is an instance of what is called the Rk4 method. It is probably the most used numerical method for solving an initial value problem. And yeah, so it's really accurate, and it's sort of the gold standard. In a week or so, we're going to go over the Euler Method, which is a really simple, straightforward numerical method. It doesn't converge as fast, but if you don't know anything else, it'll work. And so I'm putting all my outputs and my trajectory into this vector y. T just runs through time, and then this is just a nifty little thing to plot it. So let's go ahead and see what happens. So I'm running this from 0 to t equals 10. You can think of that as years, for instance, or months, or whatever you want. And h is step size of 0.01. So that means we are making a numerical guess every 0.01 seconds. And this guess is governed by this algorithm. So this isn't going to be an exact representation of our system, but it's going to be pretty close. And that's something that you're always going to run into whenever you're doing some sort of computer method like this. So let me go ahead and run it, and so we can see. So basically we start with 2 predators and 1 prey, and apparently that's not enough to support these predators, so instantly our predators start dying out. And so this is the y-axis is our predators and the x-axis is our prey, and they keep eating the prey, but then they're dying out enough until this point here where there's a few enough predators that the prey can actually start reproducing again. And so now we see that the predators have almost completely died out, but nearly an extinction level event, honestly. But then prey start reproducing a lot, and they're like, wow, it's a party. The wolves are gone, and now we can go and start reproducing. But then after they hit this point, there's enough prey that the predators can start eating them again and reproducing. And so then it kicks all the way back up, and it goes into this cycle. And so that's something that's really cool. It basically shows you the sort of cycle that happens in nature based on sort of supply and demand that happens here. And yeah, so this is the look of Volterra equations, and it'll just keep looping over and over again. This is assuming that it's just these 2 guys, and there isn't like some sort of extra term that's coming in and killing them. There are some modifications where you'll see not only this loop, but maybe you'll actually see them decaying and going to some sort of stable point. And so that's what you got. So yeah, you can see definitely that we are talking about thousands, because if you get to be less than 1/2 a rabbit, so say you have a rabbit foot, nobody buys a rabbit foot and has 3 rabbits, or 3.25 rabbits pop out of it. So yeah, so this has to be a scale of thousands or hundreds or something like that. So but yeah, so anyway, so that's the look of Volterra equations. Let's go ahead and take a look at the second one here. So there's less parameters. So here I'm just choosing a step size of 0.1 and a t of 30. So remember, this is the susceptible, infected, and recovered model, SIR model. And so this is supposed to model, disease infection and disease spread. So what we're going to see is that peak that people keep talking about, and we're going to show you how little adjustments to the parameters actually will, quote, flatten the curve. And so we have 2 parameters here. We have beta and we have gamma, and then this is going to be my S term. So this is my susceptible term, and and it's negative because it's going to be decreasing as people switch from being susceptible to infected, right? And so that's why we have the same term here, but with a positive quantity. And then the infected, as they recover, we subtract off this gamma term, and so then these guys end up recovered. So the idea is that everybody starts off as susceptible, and so we need to have, so we're starting off with 1,000 people susceptible and 1 person infected, and these are just dummy parameters. It doesn't represent anything in particular, but you know, in any disease infection sort of thing is going to work like this, according to this model, of course. And here we have 0 recovered. So what we're basically going to see is we're going to see this funneling of these 1,000 people to 1,000 recovered people, and they're all going to be infected at some point. So it's going to push play, and so let's see what happens. So we see really early on we have this big spike that happens of the infected people. We started out with, really, remember, only 1 infected person and 1,000 susceptible, and really quickly we ended up having over 600 infected. So at one point we had over half the population was infected, and if that was actually some real disease, I mean, that would be a plague. We'd lose a lot of people, because you know, hospitals can handle maybe like this much, right? So the idea is you want to keep it down to a certain level, and we see here that we have a steady increase in the number of people who are recovered, and so by this point everybody in this model has recovered, and they're healthy again. And so we see that we have this big spike in the infected, and then it just decays down. All right, so then you could say, well, how would we flatten the curve? Well, one of the things that we had here, if you look at this parameter here, beta was our sort of thing that was governing like how quickly the infection spreads. So this is a constant parameter where if it's slapped across here, basically we have x1 times x2. x1 is susceptible, x2 is infected, and we're saying that when these two groups interact, the beta is sort of the probability that you're going to have the disease spread. So what we can do is we can damp that down a little bit. We can make it so that people interact less. They stay home, they stay quarantined, they have children that they need to wait to go to bed so that they can record lectures, you know, things like that. And they wonder, why did I sign up for this at like 11 o'clock? Like, this is crazy, you know? And they wonder, all these people wonder this. Anyway, so let's say that we have people meeting less, and so let's say 1/4 less interactions. So here we switch from 1/500 to 1/2000, and so now let's see what happens. So before we had a really huge spike happen right around here, and it looks like that's not happening this time. And if we continue to watch, we see that we end up having a peak in the infected around 200 people in this community. Looks like maybe like 225-ish, and then it starts dying down. And if I let this go out further, so we can let's increase the drama. Let's see how far this goes. Let's take it up to 50. Let's see what happens. So we again are having our susceptible people. This is decreasing as more and more people get infected, but then recovery seems to be happening pretty quickly too. And so we had this peak here, and now all these people are declining as far as being infected, and they're recovering. And of course this ends up continuing to go on, and eventually this term will meet up with the 1000 here. But it's a lot less dramatic, and it's a lot less of a snap for this to happen. So we see that by decreasing the number of interactions that people have and forcing the professors to work from home, you know, the disease is better. So I guess I'm doing this to keep you healthy. I guess, yeah, so there you go. So that's a bit of Matlab code. If you want, I'll go ahead and share this up when I post the video. So I'll put it in Canvas, and you guys can go and play with this. As students, I believe you should be able to have access to a free copy of Matlab. You have a campus site-wide license through our university. Each university is different. Our university happens to provide this for our students. So you should be able to download MATLAB if you want to play around with it. I'm not going to require you to do it, but it'll certainly be instructive. And yeah, so that's fun. In any case, so I'm going to go and I'm going to take a few minutes and play Breath of the Wild on this little like Switch Lite that I picked up during the quarantine to keep myself sane. And then check out my babies and do my chores and go to bed and wake up and do it all over again. That's life. All right. Thank you for watching. And yeah, I guess we'll pretend like it's daytime again. Okay. So I hope you enjoyed the lecture that I gave in my jammies. So we went over several different differential equations. We have interruptions by cats, and yeah, the whole idea, don't worry if you don't understand it. We're going to go and do a whole lot more differential equations for the rest of this class, and I just want you to have some sort of vague concept of what's going on here. I threw in a little bit of MATLAB type stuff just so you can see, and I'll give you in the class a bunch of links that you can use to get MATLAB. Our university has a license, a site-wide license for students and faculty to use MATLAB. So if you want to put it on your computer, that's certainly something you can do. Or there's also a VPN option where you can sign in and do it through a terminal, I think. I've never used that option, so I wouldn't know. But I guess, yeah, right now we're just playing with differential equations. No stress, just we're trying to figure out what all this is. And then in the next couple of weeks, we'll actually get down to nitty gritty of like solving differential equations, which is going to be a whole lot of calculus. All right, so have fun, and yeah, I'll see you next time.